Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on Java native interface and looked at chapter 4 of Oracle's documentation on JNI, which is about JNI functions. This chapter serves as the reference section for the JNI functions. And these are the functions that are provided in the JNI environment pointer. It provides a complete listing of all the JNI functions. It also presents the exact layout of the JNI function table, right? And then again, JNI functions are the functions that we use to access the fields of an object, get the length of an array, to get access to the primitive arrays, to get or set or basically call methods in objects, call methods in interfaces, or any type of thing that we want to do a callback into Java from the native code, from the C++ code. We have to go through the JVM, which means we have to interact with the JNI environment pointer. Note the use of the term must to describe restrictions on JNI programmers. For example, when you see that a certain JNI function must receive a non-null object, it is your responsibility to ensure that null is not passed to the JNI function. As a result, a JNI implementation does not need to perform null pointer checks in that JNI function, right? So it's our responsibility to check if a parameter that passed to a JNI function is not null, and we have to also check if the return type of a JNI function, most of them return pointers. Let's say when we want to create a object, right? All those J method IDs, J field IDs, all of them are pointer types. And if we want to basically, let's say we want to create a new object, we ask JVM to create a new object and it returns a pointer. If it's null, it means JNI couldn't allocate memory for that object. It couldn't create it, right? So either an exception is going to be thrown, or if JVM runs out of memory, then the return type is null. And then we can check if it's null, it means that we ran out of the memory, we couldn't allocate objects, right? So a portion of this chapter is adapted from Netscape's JRI implementation, Java Runtime Interface. And we said that if you open up the JNI.h header file, you see that at the beginning it has a comment that the JNI interface that the JVM provides, or the JDK provides, is a extension of the original Netscape's native interface. The reference material groups functions by their usage. The reference section is organized by the following functional areas: interface function table, version information, get version, constants, class operations. We've seen, for example, FindClass. This is the main function that we use when we want to get a handle to a class on the class path. And whenever we ask JVM to find a class on the class path, we have to give it the full string, a const pointer, which is the class path description, and the separator is /, and then it returns a JObject, which is a pointer. And basically it gives us FindClass returns a JClass, which is a pointer to the metadata of that class in the Java heap, right? And then or a pointer to the meta space in Java, and then that has all the information that we need to basically JVM needs to know which class we're talking about. So FindClass and having a JClass reference is the first step in most of the JNI calls that we do inside the C++, because we have to tell JVM which class we are talking about, right? Get superclass, obviously this is very similar. Define class, we can define the identification of the class. This is not something that we clearly use. We normally don't use define class. Get superclass, this is obvious, is assignable from. This is equivalent to cast, so is assignable from. And we saw that in the when we talked about the functions that are related to the reflection API in C++, is assignable from is basically equivalent to the instance of operator inside the Java code. This checks if a object is an instance of another object, or it's assignable. Assignable means we can do a proper cast, right? If a casting is not allowed, then Java compiler will warn us, so it doesn't allow us to compile it. But in C++, basically there is no Java C, right? There is no checking, so it's all about the runtime. Exceptions, we've seen exceptions in depth, right? So it has four main functions that allows us to handle the exceptions: exception occurred, exception described, exception clean, and exception check. And then there are two functions that allow us to throw exceptions. So throw and throw new, when we want to throw a JThrowable, an object, or throw a new exceptions. And this takes an argument of type const pointer, the message, and it just throws the exception. And it requires a J class of the exception class that we want to actually throw. Exception occurred, describe, exception clear, and exception check. These are the four functions that we deal with when we want to handle an exception. We don't want to throw an exception, we want to handle them. Fatal error, I mean, the name is very easy. What it means is just a fatal error, a non-recoverable error, and we have to terminate JVM when a fatal error occurs. Global and local references, and again, these are something that we don't typically deal with, and in the past lectures I briefly discussed what these are about. And typically these, basically JVM has a limit of how many local or global references it can create inside the native code. At some point it becomes unmanageable for the garbage collector, so we have to be careful. Global references, new global ref, delete global ref, local references, and we typically don't deal with this. We typically allow JVM to handle them. But if we are creating lots of local references in a loop, for local references to, let's say we have a large array of objects and we're getting each element of that array, therefore we are creating a local reference in the native code, then we might need to call the delete local ref on them. Ensure local capacity, this is the function that we can use to set the limit of the local references that we can create in the native code. Push local frame, pop local frame, these are something related to the stack. And we can create new local references. Weak global references, and again these are for circular pointers, and again this is something that we rarely use and we rarely deal with these kind of functions. And new weak global reference, delete weak global reference. And if you're familiar with C++ and the smart pointers, you know that we can have circular dependencies with shared pointers, and this is more or less the same thing. If we want to break the circular dependencies, usually we use a weak reference instead of a strong reference. Object operations, we've seen these. Alloc object, again this just allocates a memory inside the Java heap. This is not something that we typically use. New object A, new object V. And so you see this pattern in many of the JNI functions. They have a function that takes a var parameter, new object A and new object V. And then these two are pretty much doing the same thing, but the type of parameters that they get are different. And one of them is, if you recall, we had this JValue. Let me see if I can find it. I think it's in the primitives chapter, where when we talked about the Java primitives, we saw that there is this union JValue can hold any Java type, right? JBoolean, JByte, JChar, JShort, JInt, JLong, JFloat, JDouble, and JObject. And one of these, basically new object A and new object V, one of these basically takes an array of these JValues, right? A new object is just a basically a var parameter, so we have to manually pass the types. But one of these new object V or A takes actually a array of these JValues. So, and these are unions, so any of these types can be active. So the JValue can hold any type of pointer, right? JByte or JObject, right? GetObjectClass, and this is another use case of the FindClass. So GetObjectClass, if we have a JObject reference to a Java object, we can pass it to the GetObjectClass and get the J class of that object. Alternatively, we can use FindClass to get a J class of that. Now, in order to use FindClass, we have to provide a string that represents the class path, and sometimes it's very long if our class is inside multiple packages. So if it's easier that if we have an instance of the object, we can quickly get its J class, its meta information, by calling this GetObjectClass. And usually for instance methods, we know that the JVM passes a JObject reference to that particular class object, so we can use this to get the J class of that object. And that's we need the J class if we want to then get access to a field or call any of the methods of that class. So let's see if we have, I think we talked about GetObjectClass. Yes. So here's an example that I have: J class, person class, environment, or JVM GetObjectClass person. So alternatively, I could just say FindClass and give it the string representation of the class path. But if we have an instance JObject reference to that particular class, we can use the GetObjectClass, right? This is equivalent to saying that we have a class in Java and we say whatever class dot get class. It's equivalent. FindClass is equivalent to using the actual class with capital P. For example, person, I can say person.class and gives me a J class of that class, not a particular object, right? GetObjectClass, get object reference type, and again, this is not something that we usually use. Is instance of, the name is very basically descriptive of what it does. Is instance of, again, this is pretty much equivalent to instance of method. So is instance of, right? So we discussed this when we talked about generics. We said that when we have a generic function or generic class template, and then let's say I have a function that takes any type, and then it's a native. We said that a native method or native classes, a native method can be generified, right? Can have generics, and we can bound them. For example, this native method gets a type, but that type extends number, so it has an upper bound. But number has many subclasses: double, integer, float, right? So what we need to do, and the way this is instance of works, is that we have to compare the J object, right, and then the J class. So we have a J object is instance of, takes a J object and checks if it's instance of a particular class. So we have to pass a J class reference that has the information of that class, right? Here I'm finding the double class and integer class, and when we pass a number in the C++ code, I can ask JVM or the environment pointer, and this returns, this function is instance of, returns a J boolean, which is compatible with the bool type in C++, so we can put it inside the if condition. Is instance of, this is my number, which is a J object reference, and then the J class that I want to check, which is integer class or double class or whatever, right? Is same object is also very descriptive. It checks if an object is the same object or not. And this is equivalent to the equality operator in Java, or basically dot equals equality operator. Basically, we know that if we compare two objects with the equality, basically with the equal operator, what it does is it checks the references, and if two objects have the same pointers, they must be the same, right? You can't have two objects that point to the same memory location. Basically, they have the same pointers, but they're not the same. This is what it does. This is equivalent to the equal operator. Accessing fields of objects, we've talked about this. Get field ID, get type, field routines. These are for the primitive types. Set type field is for the primitive types. So if it's a primitive field, integer, double float, we put the primitive name int double float, right? If it's the field is an object type, we put object here, right? And the entry point to working with these two functions is that we have to have a J class, and then from the J class we get the J field ID, right? Get field ID basically is a pointer offset within the J class. Within the class, it tells JVM, hey, go to this class and go to this offset. That's the pointer. The pointer is there, and the good thing is that we can cache it. So, and this get field ID is has the most overhead. We have to avoid doing it many times, because if because get field ID is only related to the J class, not the J object. So once we have it, we can use it for different objects of the same type, because this is only related to the class itself, not different objects, not different instances of that class. So let's look at the fields, accessing fields, and we said that if it's a static field, then we have to put a static after get. So get a static int field, get a static double field. And if it's an object type, if the type of the field is object, we instead of primitive type, we write object, get object field, set object field. And we said that the mechanism of the JNI is pretty much identical to the Java reflection, but then JVM doesn't do any checks on the exceptions, because all the native manipulations that we do in C++ are all deferred to runtime. Whereas we know that in Reflection API, the Java C forces us to handle the exceptions that might occur, right? But in C++, all those compile time exceptions or checked exceptions, we don't deal with them, because all of these native access to internals of the JVM are deferred to runtime. There is no Java compiler. So we said that the entry point is to find a class or have a J class handle on the class that we want to manipulate, and then get field ID. We tell the JVM go to this J class, go to this class, get this field and signature. And we said that the name of the field is not enough, because two fields of different types might have the same name. That's completely allowed. Therefore, the signature of the field or its type, each fully qualified name, fully qualified type, is also important, right? And this gives us a field ID, which is the offset pointer, where the pointer of this field is. And then for primitive types, we use get type field. And then for fields that are objects, Java objects, for example, a string, we use get object field, right? And if it's a static, we use get a static field ID, because we know that the static fields are stored at different places inside the Java memory model, right? Their actual static fields are also stored in the meta space, not in the actual class, right? So get a static field ID, and then get a static type field for primitives, get a static object field for static fields that are Java objects. So calling instance method, get method ID, and again methods, again very similar to fields. So we get the method ID, that's the offset within the class that has the address of that method, where that method is. So again, we have to start with the J class of the class so that JVM knows which class we're talking about. Get method ID or get a static method ID. This gives us a pointer, which is offset, pointer offset, and it's of type method J method ID. And then call for method, we use call type for primitives, call type method routines, call type method A, call type method V. And again, A and V, they're pretty much the same as the call type method. The difference is that they take, instead of so call type method, it just takes a var parameter and we have to just pass them. But for example, one of them, I guess V, it takes an array of J values. We know that the J value can hold any type of Java type, right? Any Java type, because it's a union. And then we also talked about the non-virtual ones, and then call non-virtual. So non-virtual. And we said that directly calling a non-virtually calling the method doesn't have the overhead of lookup, because in Java by default all methods are virtual methods, right? And we said that if we know a method has not been overridden, we can use a non-virtual, call it non-virtually, which is a little bit faster than virtually, because we tell JVM exactly where to find it, in which class, so that JVM doesn't need to check the type of that class at runtime. Call non-virtual type method, call non-virtual type method V, and call type non-virtual method A. Accessing static fields, get a static field ID, get a static type field routines, get a set a static type field. These are for primitive types, or for object types, we instead of type we just write object. Call a static method, get a static method ID, call a static method routines, call a static type method A, and call a static type method V routines. A string operations. We said that basically the problem with strings is that the Java strings are very different with native strings or C++ strings, because Java uses UTF-16. I mean, it's actually not UTF-16. It's we saw that it's actually modified UTF-8. So for ASCII compatible characters, it uses UTF-8. For UTF-8 encoding, it's still 2 bytes, but the second byte is just 0. For and then the next level is basically UTF-16 2 byte, and then 3 byte or more than that, right? And there's a range of where the how many bytes is used depending on where the binary is. So they have ranges for the ASCIIs and more than that. A string operations, new a string. This returns a I think it's UTF-8 or UTF-16. You have to check. Get a string length. This just gives us the length of the string, a string that Java knows. This is equivalent to a string dot size or something like that. So the string class has a method, and this get a string length is equivalent to that. Get a string chars. Release a string chars, and then again, the reason that we have these release functions, because when we get the strings, JVM usually creates a copy of that string, puts it on the Java heap, and gives us a pointer to that. And that's just because that copy is actually a const char pointer, so it's a UTF-8 pointer. So when JVM creates the copy, it actually knows that it has to create a UTF-8, so that we can easily use it in Java, in C++. But then it's a copy, so it's created on the heap, and when we are done with it, we have to tell JVM to delete it, right? Because any heap allocation must be deleted. So release the string, and then either release a string chars or release a string UTF chars. All right. And we said that any function, that a JNI function that starts with get and gives us a raw pointer, let's say const char pointer, it's a raw pointer, right? Has a companion release function that must be called, and usually these get functions also have a flag for is copy or not, so we can check if it's a direct pointer or a pointer to a copy, right? And we said that usually the ones that have the ones that denote critical access are actually the ones that give us direct pointers. They don't copy and then they give us direct pointers, right? And in that case, calling the release method or release function doesn't delete anything. It just tells the garbage collector that we're done with it. You're free to move it in the Java heap if it's necessary, right? So new string UTF, get a string UTF length, get a string UTF chars, release a string UTF chars. And we said that in C++ we deal with these UTF types most. Get a string region, and then if we just want to get a substring of a string, we can use the get a string region. These ones that end with region, they do copy, so we have to provide a native buffer, and they copy the Java array into the native array. Get a string UTF region, and get a string critical, release a string critical. So let's look at the critical topic that we discussed. Regular versus critical access, right? And the same thing with critical access to strings. And we said that the beauty of critical access is that it gives us a so get a string UTF chars, we pass it a J string pointer and is copy. We usually don't care, so we can pass a null pointer. This is a J boolean pointer, and it returns a const char pointer. But this is always a copy, right? It's a raw pointer, but it's a raw pointer to a copy of the actual string. But the good thing about this is that it gives us a char pointer, which means it's a compatible type. If we go with the critical route, JVM doesn't create a copy, but it doesn't give us a const char pointer. It gives us a const j char pointer because again, UTF-16 is 2 bytes, char in C++ is 1 byte. So it's a j char, right? J char is just unsigned short. It's a 2-byte integer. And then the problem is that we cannot directly use it with any C++ code that works with raw strings because raw strings are char pointers. So we have to manually do this conversion. So it's just better to ask JVM to do the conversion and give us, right? So there's really not much point in using the critical access to strings because even though we have a pointer, eventually we have to convert it to a char pointer anyways. Otherwise, we cannot directly use this j char pointer. We saw a very interesting example is that if it's an ASCII character, for example, English character, j char is compatible with ASCII, right? So which means the first character is the first character, right? J char, but the second byte is 0. And if we pass it to any function in C++ that accepts const char pointer, it assumes that the second character is actually a null character. So it only reads the first character. And that was the problem when we used, for example, we passed the const j char pointer to the C out. We saw that it only printed the first character. That's because it converts this into char pointer. So it reads the first byte, it's the first character, but the second byte is 0. Because j char, the second byte is 0, and 0 in in a string, it means a null termination. That's why we can, if we just pass the j char pointer to a cout function or any function that expects a const char pointer, it just reads the first character because the second byte, which should correspond to the second character, is a null character. Get a string critical and release a string critical. Again, it's not very useful for us because it gives us a const j char pointer, not a char pointer. All right, array operations. We said that we have primitive array types and then object arrays, right? And primitive arrays in Java are objects, right? But primitive arrays or CS-style arrays in C++ are not objects. They're just decay to pointers. Array operation, get array length for, and this is the most function that we typically use. The very first thing that we use is to have a so arrays are represented with a J, some type array for primitive types, J double array, J int array, J boolean array. For object arrays, it's the J object array, right? So new object array, get array length, get object array elements, set object array elements, new primitive type array. So new double array, and we pass it a J int. Again, note that the C++ functions, JNI functions don't take the size t type, right? They use the J int type, right? So we pass, make sure that if you pass a size t, you have to do a explicit type conversion. I think the compiler will warn you, but the compiler can do explicit casting, I believe. Although, yeah, it can do explicit casting, but it's better to do it explicitly for yourself and then pass a JInt, right? So if you call the get array length, it automatically gives you the JInt for the length of the array. New object array, get object array element, set object array element, and we said that for object arrays we have to use these. New object array and then set object array element or get object array element, and the get object array element gives us a JObject pointer, right? A JObject reference or a pointer type, and creates a local reference. And that's the one of the only places that we have to worry about local references, and we might need to manually delete those local references, right? New array, primitive types, new double array, new int array, get primitive array elements. This gives us a raw pointer. So there's a difference between get double array region, and we said that when we call a method that has ends with a region, it means an explicit copy. We're giving JVM basically C array or a native buffer, array buffer. Let's say here I create a C style array of type J double, and then ask JVM to set double array region or get double array region. When we use get, the JVM copies the J array from this index with this number of elements into the native buffer, native array. And when we use the get primitive array region, it does the opposite, right? It copies the native array into the J array. And we said that get primitive array elements, the difference here is that instead of copying, JVM gives us a raw pointer. So let's see, critical, regular versus critical access. And we said that get double array region, it's an explicit copy. We explicitly ask JVM to do the copy. We know that a copy happens. Get double array elements, it gives us a J double pointer, so it's gives us a raw pointer, but then it has this is copy flag, and when we tested it, we saw that is copy comes back true, which means that what JVM does behind the scenes with this get double array elements is that it actually clones the original array. It creates a copy of that and gives us a raw pointer to that copy. So a copying automatically happens, but because this is a raw pointer, when we're done, we have to tell JVM to actually delete that copy. So this get double array elements comes with an is accompanied by a dual function release double array elements, and we pass in the, and then we pass it this J double pointer. All right, and then what happens is that JVM just deletes that copy. So basically what happens, first JVM copies that copy back to the original array and then deletes the copy. So two copying happens, but the copying happens with JVM, not with us. So it's a little bit more convenient, but then the problem is that obviously we don't want to do copying, two copy if the array is very long. So we can go with the critical route. So it gives us a void pointer, get primitive array critical, and release primitive array critical. And when we check that, is copy comes back false, which means that this is not a copy. JVM didn't make a copy behind the scenes. This is a direct pointer to that primitive array in Java heap, and it's a void pointer because it can't correspond to any primitive type. So we have to manually typecast it. And once we're done with it, and we see that this doesn't create any copy, but we still need to call the release primitive array critical, and that's because this is the basically when we call this, the JVM actually pins down that array in the memory and tells the garbage collector to not touch it, right? So that disallows the garbage collector to touch that array and moves it in the memory when a GC is required. And when we call the release primitive array critical, again, no copying happens. JVM doesn't do anything. It just unpins that array in the memory, which means now the garbage collector is allowed to move that array in the memory if needed. Register native methods, and we saw that register natives is a very nice feature that the JNI provides. We can manually load those or register them so that we don't need to create a header bundle for that particular function. So we manually tell JVM, hey, we are registering this native method. So don't try to look for a particular header file, that header, or basically a function that has this binding type. If it's not overloaded, then the binding is something like this: Java underscore package name underscore class name underscore method name. This is the default binding of a C++ function to a Java method, native method. And that's what the JVM looks for. If it's overloaded, then it also looks for the signature of the parameters, right? But then we said that if you use register natives, we don't really need a function that has this signature. So we can eagerly register that method for JVM. And we said that we use this capability usually with the JNI on load, for example. And then because once the dynamic library is loaded in the memory, we can eagerly link those C++ functions to native method in Java, and then they don't really have to have this signature. The drawback here is that we register native, this function pointer, which points to a C++ function, basically it has to take the JNI environment pointer as the first argument and a JObject or JClass as the second argument, right? Because JVM needs to, we have to tell JVM, or JVM needs to check if this corresponds to a static method or a non-static method. And the way it checks for it is by checking the JObject or JClass. Register natives, unregistered natives. And again, unregistered natives happens if a class is unloaded in the memory, right? And again, this is not something that we typically use. Monitor operations, monitor enter and exit. I believe these are more related to the multi-threading. NIO support, new direct byte buffer, get direct buffer address, get direct buffer capacity. If you're familiar with the NIO, you know that the Java allows some direct access to the native heaps or non-Java heap directly. So these are something. Reflection support, and again, these are so reflection, let's search one from reflected method, and we said that these are for just sending a method directly, a method class that is inside the java.lang.reflect, for example, to C++, and we can get the method ID directly from a method object, right? So basically from reflected method, they get a JObject, which corresponds to basically a method object, and then it returns the J method ID. So we can directly get the method ID from the method class, method object in Java. J field ID from the field object, which is inside the Java lang reflect. And then to reflected method, we pass a J class, and then J method ID, and then the J boolean is static or not, right? And this returns a J object, and which corresponds to a method object in Java, right? To reflected field, get superclass is assignable from, and we talked about this. Java VM interface, get Java VM, and these are some functions that we typically don't use. I mean, if we want to check what are the current VM settings, we can use these, for example. So this was an overview of chapter 4, which are all the JNI functions, which is, I believe, the most important part of the JNI. And in the next lecture, we go deeper into the documentation of these functions. So I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one.